Good morning.
Good afternoon.
Good evening. We are Seth, Christine, and Michael. In this video, we'll be talking about circularly coupled Markov chain sampling.
Circular coupling is a coupling algorithm described by Radford Neal in a 1999 paper. It is a refinement of common random number sampling, where the goal is to sample from some stationary distribution pi of a Markov chain. To do so, we will reuse random numbers in a circular fashion to avoid a burn-in time. So say that we have some Markov chain with stationary distribution pi. Say that the transition function, which takes in the previous state and the random number and deterministically finds the next state, is called phi. To sample from pi with circular coupling, we first determine how long we want our circularly coupled chains to be, so let's say n. Then we generate a series of random numbers u0 through un minus 1. Next, we draw x0, the first state in our Markov chain, from our starting distribution p0. From here, we will use our transition function phi to generate the next state, x1, from u0 and x0. We continue generating until we get to state xn. Here is where the circular part comes in. We wrap around the next chain, so y0 equals xn. Then we similarly generate y1 from u0 and y0, y2 from u1 and y1, and so on. If at any time t we get that xt equals yt, then these chains have coalesced. If we generate up to yn, and yn is still not equal to xn, then the chains have not coalesced. We will refer to the sequence of x's as our original chain, and the sequence of the y's as our wraparound chain. The coupling only succeeds in y has approximate distribution pi when the chain coalesces, if and only if xn is equal to yn. If the chain doesn't coalesce, then we must choose a larger n and rerun. So if we wanted to use circular coupling, how could we ensure that it works? Assume that 1 minus epsilon is the lower bound of the probability that if two chains are started from pi, they will coalesce within n over 2 iterations. 1 minus delta is the lower bound of the probability that if one chain is started from pi and the other chain is started from p0, then they will coalesce within n iterations. Then the wraparound chain y will have a total variation distance of at most 2 epsilon plus delta from pi. The proof can be somewhat convoluted, so please refer to our paper for more details. But as a brief overview, in order to apply the conditions of our theorem, we must generate a theoretical circular coupling. After generating the original chain, we sample two chains v and w from pi. We have chain v starting with u0 and chain w starting in the middle with un over 2. We then merge these chains to form y. The box points in the plot. It turns out that this theoretical algorithm is equivalent to our circularly coupled chain algorithm when v and w coalesce by time n, which happens with probability 1 minus epsilon. Also, we need the condition that v coalesces with x by time n, which happens with probability 1 minus delta, and finally the condition that the wrapped around portions of w and v coalesce by time n over 2, which happens with probability 1 minus epsilon. After applying the union bound and coupling inequality, we can see that the total variation distance between y and pi is at most 2 epsilon minus delta, as desired. A natural question that may arise is how to find epsilon or delta, because you don't even know how to sample from pi in the first place. The answer is, unfortunately, that we cannot theoretically compute these terms. We can just practically gauge whether the conditions are necessary for the theorem to be true through empirical diagnostics, such as auxiliary chains, which are chains that are started from different times between 0 and n. They're started from p0 and use the same common random numbers as the other chains. If auxiliary chains converge quickly, like in this plot, then we can say that theorem conditions are likely true. However, generating auxiliary chains can be time-consuming. To make our chains, Neal suggests using a parallel computing method. The computation time is bounded between the time of sampling n over r and 2n over r iterations of a standard Markov chain. That is, if the auxiliary chains converge. It has unbounded computation time if the chains do not converge. So this algorithm has a few pros and cons. The pros would be that there is indeed no burn-in time, so there's no bias introduced from removing the burn-in states. Also, Neal's recommended diagnostic of multiple auxiliary chains are more rigorous than just using one series of common random numbers started at the same point. That being said, Radford Neal may be at the cutting edge of MCMC research, but there may also be quite a few reasons why this is one of his less cited papers. There are quite a few cons of circular coupling. One would be that it's near impossible to theoretically bound the accuracy of chain y. The dependency of the algorithm on chain length n is also inconvenient. Since we cannot find the theoretical bound, it's also hard to determine or adjust n if the algorithm doesn't converge the first time around. Finally, it's generally pretty tedious to implement and check this. Between the potential error of Y's distribution and the computationally expensive diagnostic like auxiliary chains, there may not be a huge edge over just running your standard MCMC method with a burn-in time.
So now that we've talked about circular coupling and talked about the pros and cons, we of course will want to implement that. So we might imagine starting with something really simple as the Markov chain transition that we'll be using. So for instance, random walk metropolis. We'll be choosing a proposal distributed uniformly at random within a distance w of our current state, We accept it with the traditional metropolis probability as opposed to metropolis Hastings, because we assume that the target distribution is symmetric. And that's nice in the sense that the transitions are easily computable, but there's actually a probability of 0 of exact coalescence just because we're pulling from a continuous distribution for our proposals. So instead, one way we can get around this is something called random grid metropolis. What we'll do is at each time period, we're going to discretize the space into a grid of points that are spaced apart with a distance of 2w. And then we're going to choose the location of that grid at random, and our proposal is going to be the nearest point on the grid to our current state. Here's a bit of a visual representation of that idea. We have here the current state and the state space. We choose a location for the grid. We populate the grid to have a distance of 2w between points. And we pick the nearest point on the grid to the current state to be our proposal. So this has the really nice property that the proposals actually still follow the same distribution as for random walk. That's because it's based on the location of the grid, but it'll certainly be within a distance of w of our current state, and that's distributed actually uniformly at random as to which point there it'll be. At the same time, because we'll use the same grid for any of our two chains, we have a positive probability of exact coalescence. And of course, we still accept with the same probability that you see there. Here's a bit of notation to formalize this. This F is the proposal that we make, and this phi is the next state. So you see that the next state will either be our proposal or the current state again, based on whether or not we accept or reject. This F may be a little bit complicated to understand, but here's how we'll break it down. So the U0 from the U0 from the last slide is essentially the coin flip for whether or not we accept. That kind of makes sense. And the U1 determines the grid location. One way that we can see this is by thinking about an F tilde that looks as follows. And we can clearly kind of interpret this as being taking a grid centered at 0 with distances of 2w still, and basically picking the point on that grid that's closest to our current state x. But if we actually want to locate the grid randomly, what we can do is subtract a random variable, a uniform random variable centered at 0, like u1 minus 1/2, from our x over 2w before rounding and add it back afterwards. And that is what allows us to randomize the actual location of the grid. So we also implement this one-dimensional random grid metropolis using a standard normal distribution as the target distribution. This line in red is the original chain, and the line in blue is the wraparound chain. You can see that they converge, they coalesce very quickly as desired. We can also plot a histogram of the wraparound chain final points or final states over several different simulations, and plot the normal PDF as well, and see that it matches up very well. And then finally, we can, like Neal does in his paper and like we talked about before, also do the auxiliary diagnostic chains and see pretty quick coalescence, which implies that we've kind of converged to the distribution that we want. Finally, we don't just have to work in one dimension. If we have multiple dimensions, we could still just simply update individual components one at a time, or we can do kind of a multi-dimensional grid idea. So now our U is actually going to be several different uniform random variables as opposed to just 2, and for each component, we're going to use an F like what we had seen before. What this means is by picking the closest point along several dimensions, what we're really doing is we're constructing a multi-dimensional grid and just taking whatever point is closest on that grid to our current state, where again this grid is chosen uniformly at random in terms of its location. So neither of these two strategies, neither single component nor our multi-dimensional grid, is better in every situation. So for instance, Neal does a 9-dimensional multivariable normal example where the single component idea is better, but he himself remarks that that's kind of just by luck that that occurs. But both tend to reduce the distance between distant chains, and neither are necessarily good for chains that are already pretty close in terms of reducing the distance. We do have a positive probability of exact coalescence when they're sufficiently close, but we don't get to reduce the distance necessarily to where we want it, which is why we often combine this random grid metropolis idea with other transition possibilities.
Random grid metropolis updates are capable of causing exact coalescence, and the probability of exact meeting increases as chains get closer together. However, random grid metropolis on its own is not a very efficient way of sampling from the target distribution, and is also not the most effective way of bringing chains closer together. Other sampling methods are needed in order to make sure that chains end up coalescing. Therefore, Neal introduces the following practical strategy for circular coupling, detailed on page 27 of the paper. This has two steps. The first step is an update or series of updates that is designed to efficiently sample from the target distribution, and that is coupled so as to cause chains to approach closer together. The second step is a random grid metropolis update, which can lead to exact meaning of chains that are already close together. For the next few minutes, we'll discuss both step 1 and step 2. Let's start with step 1. As a refresher, the two goals of step 1 are to bring chains closer together and to sample from the target distribution efficiently. For Neal's circularly coupled methods, there are a few requirements. First, all methods must use common random numbers, and more than that, they must use the same number of common random numbers per update, irrespective of the state of the chain. This is because to circularly couple the X chain and the Y chain, you need to have the X chain and the Y chain use the same common random numbers. If you don't know how many common random numbers you're going to need for the X chain or the Y chain, there's no way to guarantee that they're going to be able to use the same numbers. For step 1, Neal considers three algorithms. The first is random walk metropolis, the second is the metropolis adjusted Langevin algorithm, and the third is Gibbs sampling. The first algorithm that Neal considers is random walk metropolis, which is a good candidate because there are only two aspects of randomness per iteration. The first is drawing the symmetric proposal distribution that is centered at the current state, and the second is accepting the proposal based on a draw from a uniform random variable. Therefore, it's an obvious candidate for circular coupling. Unfortunately, random walk metropolis is not the most efficient in bringing the chains closer together, as we can see here from Neal's paper, where he uses a 9-dimensional target distribution drawn from a multivariate normal, and uses random walk metropolis to try to bring two chains close together. We can see whether or not you're doing single variable or multi-dimensional updates. It takes around 10,000 to 100,000 draws and iterations for the chains to get around -2 to -6 in terms of log squared distance apart. We'll see significant improvements on this with other algorithms, for example, the metropolis adjusted Langevin algorithm. The metropolis adjusted Langevin algorithm, similar to the metropolis algorithm, has two steps of randomness. The first is in step 1 of the algorithm, where we replace p according to a multivariate normal distribution, and the second is in step 5, where we accept a proposal based on a uniform random variable between 0 and 1. There is an alternative formulation of Mala which tends to improve efficiency, which replaces step 1 in the box with step 1 that is outside of the box, but at its core it's also just a draw from a multivariate normal distribution, and so it's also a good candidate for circular coupling. Using the same problem as before, Neal evaluated Mala sampling relative to metropolis sampling and found that the chains got closer together with fewer iterations. You can see that the chains reached a log square distance of -2 at around 600 to 700 iterations relative to the 10,000 to 20,000 that it took for metropolis. Using the second version of Mala, we see even better results. You can't even tell the difference between the chains visually at around 200 iterations, and the scale of the log square distances, instead of ranging from around 0 to -2 or -4, ranges from 0 to -30. When it comes to bringing the chains close together, Mala does an incredibly good job when we use its second version.
Gibbs sampling isn't changed much by circular coupling. We use inverse sampling with the conditional CDF on a wrapped around series of random numbers. Pictured here are the circularly coupled chains and auxiliary chains of a multivariate normal Gibbs sampler.
To demonstrate how circular coupling might work in practice, we implemented a logistic regression model that Neal suggested at the end of the paper. The response variable C takes on 3 values, and X is a real valued predictor matrix that is 150 by 4. then the probability that Ci equals k, where k is in 1, 2, or 3, conditioned on the X matrix, is given by the following logistic regression equation. As is typical in Bayesian problems, there are priors that are put on the data generating parameters, and you can see a hierarchical structure here where the tau stars generate the tau j's, which in turn generate the bjk's. We generated the X matrix by sampling from a multivariate normal distribution with mean 0, variance 2, and correlation 1/2 between each of the predictors. Then we chose some true data generating values for the betas and simulated the response variables. The goal then was to reconstruct the posterior distribution of the betas given our response variables. To do this, we used the following algorithm. The algorithm that Neal suggests uses Langevin updates and random grid metropolis updates along with some Gibbs sampling updates in step 1 to bring the chains closer together. In step 2, we perform one random grid metropolis update in order to try to make the chains meet. Then we do some Gibbs sampling updates and replace the momentum variables in order to restart the process. Note that running this algorithm once consisted of one iteration of our Markov chain. We ran our Markov chain 100 times, and what you're looking at now are the trace plots of each of the individual components. We found that the components were able to get close together at around 20 iterations, but it took until iteration 85 for the chains to actually meet. However, once they were coupled, they were faithful. There does appear to be some moderate issues with convergence, especially for components 8 and 9. You see the zigzag pattern that accompanies HMC that hasn't been properly tuned to the stepwise size parameter. However, the fact that our chains met is a good sign. It means that they are circularly coupled, and the Y chain does approximately follow the stationary distribution of the posterior distribution. If we wanted to do inference, we could just take the Y chain and not worry about discarding burn-in.